Hello, everyone. I'm Rushi Sun from the University of Adelaide, Australia. Today, I would like to present our recent research, Snipuzz, black box fuzzing of IoT firmware via message snippet inference. Here, I present on behalf of our first author, Xiaotao from Firmware University of Technology, Australia. And this research has also been supported by the Data61 Australia. So the number of IoT devices has risen exponentially currently, but there are more and more security issues that follow. For example, the Mira botnet, which targeted on the CCTV cameras, and also the FDI confirms that the cardiac devices can be hacked. And also the hacking risk leads to recall 500,000 pacemakers due to the patient health fears. So in a short word, the IoT devices, because it communicate with the outside world through the internet, so its attack surface could be larger than the traditional device. And to find the potential vulnerabilities or bugs or even crashes, the fuzz testing is a very popular technology that has been widely used in various fields over the years or decades. The core solution for fuzz testing is to continuously feed the mutated, malformed, or unexpected inputs to the target in order to trigger a crash. However, existing IoT fuzzing methods rely heavily on obtaining the firmware of the device. And the firmware is difficult to obtain. No matter it is using static analysis method or even dynamic analysis method, they all need to obtain the firmware at first. So that's a challenge to the IoT fuzzing technology. And further, existing fuzzing method can now test the firmware of IoT device while. For example, for typical fuzzing algorithms such as the AFL, very famous fuzzing tool, it's difficult to generate input that meets the format requirements. For example, input validation or sanitizer, which makes the samples being rejected at a very early stage, even not enter the functionality code. And it cannot insert the instrumentation into firmware because the firmware is on the hardware, and so that it cannot obtain coverage information to evaluate the performance of the fuzzer. So there is grammar-based fuzzing algorithms. However, it needs a lot of learning materials to extract the grammar rules from these materials. And they only support for known format, that is, depends on what learning materials has been collected. So our goal in this research is to provide a black box fuzzer that can efficiently test IoT devices firmware and without the support of language learning materials. So that to propose such a black box fuzzer, we have faced several challenges. The first one is lack of feedback mechanism of the IoT device, because it is unable to obtain internal execution information without firmware. For example, in the black box scenario, it is hard to gathering feedback from the internal execution. And the second one is the randomness in responses. Even the same input may get different responses from the IoT device. For example, there could be timestamps and tokens contained in the response to information. So even we use the same input, we can get different outputs. And there are diverse message formats used in the IoT devices. For example, JSON, SOAP, key value pairs, and even customized strings. So in our research, the key contributions are: the first, we proposed a message snippet inference mechanism based on responses. And then we infer the relationship between messages names and code execution paths in firmware. And our proposed Snipuzz performs more effective in IoT fuzzing. the number of response categories explored by SneakPass is far exceeded the other message on most devices, which can be indicated by our experimental results. And they implemented the IoT fuzzing in the lightweight, and we found 5 zero-day vulnerabilities in 20 devices, and 3 of them could be exposed only by Snippuzz. So before we dive too deep into the fuzzing, I'd like to first show an example of IoT device workflow. So the input will first be entered into the sanitizer, which is somehow like an input validation module. So it could be matched by the regex, and say if the input has matched the grammar rules. If it is not, it will trigger a send message function with the parameter 0. That is like an error report. So if it is satisfied the rule base, grammar base, and it will enter into the functionality code. First, we will face a function switch. So for trigger the corresponding functionalities. Otherwise, the error message will be sent with a parameter -1, for example. And the corresponding function has been evoked. It will go to definition of the function and execute one main line. And if it's successfully executed, it will send back a message, for example, with parameter 2, 3, 4, and 5. So all this send a message function has actually triggered in the replier module, which will send back the message or the status of the execution back to the caller. For example, -1 maybe is the error message from the function switch, and the 0 related to the error message of the grammar rule matching. And other numbers may be related to some function that has been successfully executed. So as we mentioned, we have facing 3 challenges, main challenges, and we try to provide solutions to each other. To solve the challenge 1, lack of feedback mechanism, we're thinking about to use the response of the device as the feedback to guide the fuzzing process. However, the correspondence between the firmware execution and the response messages cannot be directly extracted. So we deduce that if the 2 inputs get different response messages, then the 2 inputs may go to different firmware code execution passes. And to solve the challenge 2, the randomness in responses. For example, if we use the same input A, that to execute in the firmware, however, the response message could be different, as there could be a time step inside the response. So whenever we use input A, we will always get a different response. So our solution is to use similarity algorithms to avoid misclassification caused by randomness. So the similarity score has been calculated based on the added distance, and we normalize it. So the specific step is, at first we compute the self-similarity for each response number as I, response I. So this score could be smaller than 1 because there could be some randomness in the response. And then for each new response, we name it J, we categorize the response according to the similarity score. For example, if similarity I and J is larger or equal than the self-similarity of response I, then J will be assigned to I's category. So every time we facing a new response, we will first assign to its category. And the solution to the challenge 3, diverse message format. We try to adapt our proposed method, Snipuzz, to kind of any message format. So the method is to mutate a valid message byte by byte, then merge the snippets according to the responses. Concurrently, if mutations on two different positions receive the same response, the two positions that may have a high possibility that they are actually related to the same functionality in firmware. For example, we have a message. The valid message is M, original message. The content is on true. And we mutate these characters, byte by byte. So for the probe message 1, we remove the brackets, left brackets. And for the probe message 2, we remove the right quotation. And for probe message 3, we remove the character O. And then in this way, we can get 11 different probe messages, as there are 11 bytes in this original message M. And we collect all the responses of these 11 messages, and we then we categorize based on the content of the response. For example, for the first two probe message, we got the same response, so we assign it into the first category. And for the probe message 3 and 4, we got different messages, so we assign to category 2 and 3. And for other probe message from 5 to 11, we all receive the same message, same as the category 1. So we assign to category 1. So after we collect all the 11 probe messages responses, we can categorize the snippets into 3 different categories. However, the issue is we can take a look at the probe message 3 and 4, which removes the character O and N. However, actually the O and N should have the same semantic segmentation because they have the same meaning, this part. But in this method, we will assign it to different category. So to solve this problem, we further conducted a hierarchical clustering that we convert our response message into vectors, feature vectors. We extract the features from responses. The features including the self-similarity, the length of string, the number of alphabetic, numeric, and symbol segments. So we convert each response into a 5-tuple features and perform the hierarchical clustering. So at the first round, as cluster 2 and 3 are the nearest cluster, so we merge them together into the cluster 4. And in the second round, the nearest cluster is the cluster 1 and 4. So we merge cluster 1 and 4 together to create a cluster 5. This will loop until all the clusters have been merged into one at last. So after conduct the hierarchical clustering, we will have create new snippets. For example, the snippet 5 and snippet 4, right? Which may introduce more semantically identical consideration into the snippet categorizing. Yeah. Okay, so this is the overview of our framework. We collect the initial message as C's from the API document of the IoT device, or the sampled apps of the IoT device from their official site. And we put all the seeds, the message into the corpus here. At first, we do the initial determination, that is mutate the seed message byte by byte and create the probe messages, send it to the messenger and communicate with the IoT device and collect their response. So if we have, for each new response, we will do the categorizing and put them into the response pool. So if we find a new category of this response, we will add this response into the seed pool. After we do all the initial determination, for example, we collect all the 11 probe messages from the message onto, we will select a seed from this corpus and start to the hierarchical clustering, which will create new snippets based on the semantical identical. Then the mutation module will start to work, and we mutate the message, the seed, based on the snippets. Then send it to the messenger and send it to the IoT device and collect the response and check whether their crash has been triggered. So in our evaluation, we first tested the performance of the proposed SneakPass. We collected 20 devices, all customer IoT devices from both online and offline markets worldwide, and covering various well-known brands. Include 8 different device types, including the smart bubble, the home bridge, and routers, network camera, and from 16 different vendors, 8 different formats, including JSON, SOAP, key value pairs, or even customized bytes. To know that 5 devices have randomness in the response, so it's quite prevalent. So this is the vulnerability detection result. From all the 20 devices, we found 5 zero-day vulnerabilities, including null pointer exceptions, denial of service, and unknown crashes. 3 of them could be exposed only by SneakPass. We have do a benchmark experiment using the very famous IoT father, the Duna, Bufas, and also Menzies. And we even create a scenario, we call it SnippuzZ without snippet determination. Yeah. So we can see that SnippuzZ is outperform than other state-of-the-art tools with respect to the vulnerability finding. And we further do a runtime evaluation to check the runtime efficiency of each tool. We can see that the SnippuzZ gradually discovers more categories than IoT father and other baselines. Outperform the best on 19 devices. However, we have to mention that to initialize the seed pool, we have to pay a lot of manual efforts. That is to extract the seed from the API documents or the sample tools, apps. We are now considering to automate this process. That maybe we can develop a crawler or some smart tool to extract the seeds automatically from these materials. And secondly, if the communication of the firmware is encrypted, which means that the semantic meaning has been missing, lost, then the effect of using SneakPass directly is not ideal, because we are still based on the semantic segmentation to determine the snippets, then mutate based on the snippets. And the requirements on detailed response. So because we are based on the semantic interpretation of the response, so if the response or say the feedback information of the IoT device is not detailed enough, contain the meaningless information, it's really hard to determine the snippets in the proper way. However, as the feedback, the purpose of feedback is actually to be read by human or by developers. It's not a very big deal, but maybe more work could be done on this part. And this is the reference of these slides. And thank you for watching. If you have any questions, please ask. Thank you.